So thank you guys for stepping out and coming out to our little talk here. Our talk is on dynamic compute options. We'll introduce ourselves here in a moment. So my name is Mike Enzer. I'm the VP of Delivery for Dev9. I have been in the industry for about 24 years. I'm a very early adopter of Google. I was on the original beta program for Google App Engine, so that's just kind of some of my background. I also I'm a certified architect with Google. I was number 170, so my little joke is we've got about 25 certified engineers, and there's about 2,000 certified, so we have 1% of the world's population of the certified engineers. So anyway, I want to introduce Michael. Michael's going to be starting off the conversation here. So you want?
Good morning, everyone. As I said, my name's Michael Gutteridge. I'm with the Fred Hutch Cancer Research Center. I've been there about 15 years now, running HPC at various levels. Introducing the Fred Hutchinson, our mission is the elimination of cancer and related diseases as a cause of human suffering and death. What's not on the slide is that about 2015, our president gave us 10 years to reach this goal. So that's an ambitious goal, but we have over 300 faculty and over 3,000 employees that are all focused on reaching this goal, so I feel pretty confident that we're going to get there. Our research has expanded beyond just cancer. We're starting to find links to viruses, the role of the microbiome in the development and progression of cancer. So the research area expands with every passing day. I'm part of the scientific computing team. We're a small team of about 7 folks. We're responsible for supporting our researchers and their compute needs. We support almost a full stack compute hardware, the software, the tools, as well as some high-performance storage. So we have a smallish cluster, about 1,200 cores, over 510 systems. Right now, we're running about 1.2 petabytes of data that grows by 24 terabytes every day. We have some miscellaneous systems, large compute nodes that we use for casual prototyping work and some other miscellaneous functions that aren't satisfied by the cluster. But it's a pretty diverse environment, and it's a growing environment. So the core of our talk is high-performance computing. What is high-performance computing? Well, at the Hutch, high-performance computing is pretty much computational resource beyond what's available under your desk. We scale horizontally, meaning we use commodity hardware. We just add more hardware as we need more capacity. It's what you might call a Beowulf or a shared nothing style cluster versus something like a Blue Gene, a Cray, or one of those more exotic machines. Why do we need it? Well, we've got about 7 years left to cure this cancer problem, so we need a lot of compute. We're answering and asking a lot of questions that require a significant amount of compute capacity. So how do we use HPC at the Hutch? I've just picked out three research projects here. Give you a quick introduction to what sort of work they're doing. The Optides Project is a collaboration that identifies new drugs and therapies for very treatment-resistant tumors of the head, neck, throat, and of the brain as well. One of their key problems is how you get drugs across the blood-brain membrane to deal with brain cancers and other diseases. They're a very diverse project. They work with a lot of proteomics data. They use a lot of genetics data, high-throughput sequencing-based calls and alignments, as well as protein structure and functional predictions. Just to give you an idea of the scale of their work, they've used 141,000 CPU hours since the 1st of May. The Malik Lab is run by Dr. Harmat Malik. He's part of our basic sciences division. I've read through his research, his area of research twice, and I still don't entirely understand it. He's basically looking at the problems that can be classified under genetics of evolutionary conflict. Does a lot of de novo genome assembly, so new genomes come in, they try to put them together, figure out what's interesting about that, how they've changed. Short read mapping, single nucleotide polymorphism discovery. They're probably on a smaller scale of compute for the center at about 11,000 CPU hours since the 1st of May. And finally, the GECCO project. This is a really large project. It's been ongoing for a number of years at the center. We've got about 40,000 participants in this one, and this one is basically aimed at colorectal cancers and how the environment affects your risk for getting a colorectal cancer. They do a lot of work with whole genome, so they do a lot of work looking for new genotypes in the existing data sets. G by E, which is genetic versus the environment, how the environment affects your genome, and then how that transfers into your risk of getting a cancer. Like I said, they're one of the larger projects. They have used about 205,000 core hours since the 1st of May. So, with an institution this large, we have a very diverse tool set. We have a few of the big ones. Our bioconductor is our meat and bread and the first-class tools that we maintain. We're getting more interest in machine learning these days as we move into more clinical data. Then we've got the old workhorses, SAM tools, Picard, things like that that do your traditional genetic analysis. We've also got a lot of custom pipelines that are being built at the center where people are trying to chain together different tools using a variety of systems, scripts, more modern things, Airflow, et cetera, to chain together various tools to answer their problems. We maintain all these using a couple of things, easy build and LMod, that lets us sort of build our tools in a reproducible manner, as well as deliver them easily to our researchers. So, discussed the cluster at the beginning of the presentation. We're a big Slurm shop. We've been using it since the early 2.0 days. It's an open source project that began at the Lawrence Livermore Labs. It's a very high performance solution that's used on, well, as you can see there, 6 of the top 10 supercomputers. The emphasis on performance is, well, it's a key part of how they develop and how it's been very useful for us. The big system tuning guide indicates that they had almost 2 million tasks on 122,000 compute nodes, and they started those in 322 seconds, which is fairly impressive. A little bit more down to earth, 30,000 tasks on 15,000 Linux nodes, and that took 30 seconds. So we're looking at a very high performance solution for managing and distributing workload to a cluster. Unfortunately, this comes with some costs. To get this kind of performance, all the nodes in the cluster must share the same configuration. They all have to know about each other. You can't have nodes just joining randomly throughout the day. So the cluster has to have consistent view of what the rest of the cluster looks like. So when you add or remove nodes, this is a disruptive task where you have to sort of reconfigure the cluster and tell everybody that there's a new configuration. We decided we really needed to keep with Slurm. Like I said, it's a key strategic component of our environment. We don't want our researchers to have to learn a new job submission system. And we wanted them to be able to just use their existing scripts, run with the same commands, same options, things like that, whether they were running on premises or into the cloud.
You probably want to make a real quick note there. Slurm, the partner, the company that builds and develops Slurm actually did a partnership with Google and did a kind of an alpha release of a dynamic, basically build up a cluster, do your work, and tear it down. That still hasn't really been released yet, so we'll cover that in a little bit when we get into more of the technical side of it. But it's important to kind of note that the challenges we had really were the fact that the configuration has to be known ahead of time once you build your infrastructure, so the cluster can communicate. There's no cluster communication amongst new nodes. Sorry. Right. Yeah. There are a number of ways of doing this, and since our approach, we didn't want to change anything for our community. We had to tie into a lot of resources that are back on campus. So that's a big, what do you want to call it? A big boat anchor on using the cloud is that we have to tie into a lot of on-campus resources. I don't know how many of you have worked with or are familiar with Slurm. It's pretty straightforward. You've got a controller in the middle. You've got your daemons that run on the individual nodes that accept work from the controller, and then you have a database daemon that sort of sits in the background and does all the accounting work and keeps records about what jobs were run and what jobs are running. There's a few different commands for interfacing with the cluster. They're sort of listed up there. srun, sbatch, scancel are one of the ones that just allow you to dispatch jobs to the cluster, cancel them, or see how they're progressing through the session. There's 2 options. There's a batch option and an interactive option. We do have a lot of users that use a lot of cores interactively where they will fire up a job and just from a shell fire off
various R tasks or things like that. So it's a very, very diverse workflow throughout the center. Data management here, where's the data? Well, it's all on campus. So right now we come back to the campus from our various cloud clusters to read and write data. That's a bit of another anchor and another constraint on our design, as well as the fact that we're still using LDAP and the Kerberos authentication back to on-campus hosts. So that's the problem. We have a tightly coupled, infrastructure-dependent computing environment, and we want to take that and replicate it in the cloud. So ongoing cloud is going to be a big part of our computing strategy. We are adopting sort of a cloud-first approach to computing. It gives us a lot of options, allows us to scale capacity on demand, and then scale it back as circumstances warrant. We also get new options and new technologies easily and quickly, rather than having to wait to provision things on campus. We've deployed into another cloud provider. I'll leave it to you to guess which one. And that's been moderately successful, given the constraints of having to use on-campus resources for data access. But for some work where we're doing a lot of simulation, it's been highly successful in being able to give people the capacity they need to accomplish their goals. So what we wanted to do next was expand into GCP. There's a lot of exciting things going on there. There's some new capabilities, different ways of managing resources. So it's fairly exciting to approach Google and see what we can gain from there. There's a chance for us to really diversify our infrastructure, as well as sort of mitigate any of the risks that might come along with having a single vendor solution for our cloud computing. But how do we solve this problem? We didn't really have any experience with GCP. We've been working with Amazon for quite some time. So we want to make this happen quickly. We want to use best practices. We want to have a solid deployment, but we don't really know what they are for Google. So this is where we look to bring in a partner that had the experience with Google to help us get the solution. We have Dev9, a Google subject matter expert, experience with GCP, with biology, healthcare, and as well as being Northwest neighbors. So at this point, I'll turn it over the podium to Mike Inser.
All right, so as Michael had mentioned, we're a partner here with Google, and nice thing is I get to mention this. Every time I go to downtown Seattle, I drive by their campus. They have a big sign. It's a cool campus. So it's nice that they're kind of in our backyard. We do have our company does have some healthcare and research background as well, so for some of the solutions that we've built. So I'll just go this real fast. Who are we? We're Dev9. We're a custom software development company based out of the Pacific Northwest. We kind of introduced ourselves into the cloud world about 6 or so years ago. At that time, we realized cloud was not a trend, and we still stand by that. We think it's going to stick around for a while. So that kind of got us into the game. We started working with Google about 2 years ago and became a premier partner. We've got 25 some certified engineers. So when coming here to get introduced to Fred Hutch, it was actually a really awesome time to be able to share how we build infrastructure and how we build out our solutions, and we do it slightly different, at least we think we do. And we'll talk about kind of what that solution is here. So kind of recap some of what it is that we were trying to accomplish here, like what the problem we're trying to solve. We had some kind of unique constraints. They have 400 some projects going on, thousands of researchers around the world who are actually using these tools, and we didn't want to interrupt that. We didn't want to change that world for them. What we wanted to give them is just a different option, a command line switch for them to say, I want to try a different cluster or work with a different cluster. Some of the unique things we ended up coming up with, so we get to use all the Skylake. So a lot of the performance actually is coming out to show pretty strong. So this is what we started out with. When we jumped in here, there was already an AWS implementation. Michael and his team did a great job at putting that together to kind of show the two sides. It originally started, as you see in the bottom portion of the diagram there, that was the original. Everything was on-premise. Everything was set up to be network storage arrays, and whatnot. That's where all the data actually lives. It was expanded into basically an almost exact copy into AWS and tied together with a VPN. Where possible, they dropped in bucket storage for S3 and other types of technologies there. So before I get into like what we did for our side of it, I kind of want to maybe take a small step back and talk about what is multi-cloud and why their approach, like why we agree with their approach, and we consistently work on, or we have a lot of clients who end up approaching both AWS and GCP, maybe a little Azure here and there. Anyway, so what is multi-cloud? I think you guys have heard this multiple times on the keynote. I'm not going to go too deep into that itself, but I think an interesting note to see here is that a research that just came out, 81% of enterprises have a multi-cloud strategy. A lot of the time they say that other cloud is a private cloud, but they generally will pick a private cloud internally and then they'll expand it out to one. We're starting to see that trend change, and we're starting to see more cloud adoption on multiple clouds, so it's not just one. And that's where we start building the tools that we need in order to be able to facilitate and interface into the different clouds. There are some big benefits. One, avoiding a vendor lock-in, and in a moment I'll describe that as also being a negative too. But avoiding vendor lock-in, so if you need to move your applications around or your compute around, it's easy to do. It's nice when there's outages. If you're the one company who's still able to continue to do their work when somebody fat fingers S3 and it goes down, you know, it's kind of nice. Also, with multi-cloud, you get to take the best in breed tools for each of the different vendors. And I think that's an important piece to think about. Vendor lock-in's okay if you're using it for the right purpose. So if the tool, and you know, for example here, we're going to now enable the researchers to start using things like Genomics API, which they technically didn't really have an easy access into. Now that we start having that relationship with Google, that data is closer, they can start using the APIs. So that's a best in breed type of a tool. So there are challenges to doing multi-cloud, and I think this is kind of a cool little Venn diagram I drew up here, where like when you get into it, if you really only want to be completely agnostic, you end up with the lowest common denominator, meaning that you're only doing compute, you're only doing network, you know, and well, that's about it actually. So if you want to use any of the cool features and functionality that come as a managed provider, they're just not available. So keep that in mind when you're thinking about where your strategies are with doing multi-cloud. It also does increase maintenance and governance. So you have to maintain multiple different platforms, and that means it's also operationally, now you have folks who have to, you know, teams who have to understand all the platforms, and that can be a challenge to a lot of companies as well. So how do we go about doing this? We end up, you know, as an industry, we've built the tools now to allow us to kind of have a little bit of a homogeneous infrastructure. We heavily use, we're very big fans of HashiCorp in general as a company. HashiCorp has a product called Packer. What it allows you to do is it allows you to define what you want an image or a virtual machine to look like, and it will build that image for you and either push it into the cloud you want to or build it within the cloud you want to. So with that, we can have the same base level of an AWS image, we can have the same one in GCP and the same one on premise. Largely with just the same file, and you just run it with different providers. So that sets us up for to create a base level at that point. Then on top of that, we look at what other binaries and applications need to be on those machines. One of those in this case here, a lot of the Slurm in the cluster, a lot of the Slurm daemons and those types of things, applications have to be on each of the different machines. So in that case, we actually use Chef. Chef is a great tool for configuration management. It allowed us to write once and use in multiple different environments. We as a company, we expanded this into with Fred Hutch here, but as a company, we embrace infrastructure as code. It's something that we think that every company needs to do, and we basically automate everything is kind of my little tagline. I talk about that way too much, but it needs to be said. So when we came in for Google, and this is very specific to Google, we wrote, I'm sure all of you guys, if you've done stuff on Google, you immediately know that it's not the easiest thing in the world to start with. You get a whole pile of docs, you say, now what? What we did is we wrote a foundation layer. We used Terraform. So what this does, it allows us to spell out what a base network and project structure looks like within a Google project. So We can run this with a, we set it up real simply, and it defines that so we can move projects around should we need to in a folder structure. It also sets up identity management into a layered structure, so we can do organization folders and projects in a hierarchy. So that foundation gets run once, sets it up. Then we have what we call our services layer, and this is where we actually provision managed services, such things as Cloud SQL or other dependent applications or other dependent managed services that need to exist within the project. And then at the last layer, we actually have an active, we call it the app layer, and this is where you're actively installing or updating or changing, deploying, rapidly changing services within your infrastructure. I don't think I had on the next one. Nope, I'll say it anyway. So one little tip that we like to try and say at all of our talks is when you're using infrastructure as code, if there's a possibility to run it in a continuous integration environment, definitely do that. Terraform is another HashiCorp product. What it does, it allows you to be declarative about what you want your infrastructure to look like. So you can say, I want, this is the type of machine I want 200 of them. And it's just a variable. You change that and you run it, and it allows you to declaratively or give a declarative format for what your infrastructure is. When you run that with a CI, it means that you no longer have an individual who has to run it off a laptop or even on a jump box. You now can have the same run happen every single time. It's all the benefits you get from running a CI/CD. Kind of a little side effect of that as well. Terraform, when it builds your infrastructure, it creates a state file. So it knows what your infrastructure looks like without having to go necessarily back to the cloud, so it can kind of manage itself. Now, along with that, the benefits are if you want to heavily govern, or you want to govern your infrastructure so you're not running high cost, or you want to make sure that individuals only have certain access, you generally don't want to give access to the console or to gcloud, which is the command line tool. So use Terraform to make all your changes. It forces you to run through a pattern. When you're using a CI, it runs a pattern that you actually get to do all of your own code reviews on your infrastructure going out. So you know exactly what your infrastructure is at any given time, and you can say, a change doesn't go through or whatnot. So I talked about our base images. So in our case here, our base images, everything is using Ubuntu. You guys use some CentOS? No, it's mostly just Ubuntu.
It's all Ubuntu.
Yeah. So the general idea here is that you create an image, and that image is being pushed out. I kind of already talked through that. So here's what the provisioning kind of looked like for us. We kind of started out with a base OS image, and we used just really nothing on it. It was really vanilla. On top of that, depending on the different machines themselves, a lot of them needed to have the tools that the researchers were using. So, for example, the SDK for R, SAM tool, TensorFlow, et cetera. By the way, TensorFlow is something that we are currently looking into, just saying, can we add that on as being, or at least add on GPUs into these clusters. We haven't done that yet, but it's on the roadmap. All right. And then at the very top, you have all the Slurm dependencies in it, working with it. Another thing that was kind of a challenge that we had to fit is all of the data, we said it multiple times, but all the data actually was back at HQ. So researchers throw all their data, everything comes in, sits on net storage, and then we use NFS to transfer it out to the cloud for the actual compute itself. So there are some challenges in that solution as well, just due to the latency that happens with moving very large amounts of data. All right, actually I already covered this, so I'm going to skip that slide. All right, so largely the solution itself from a technology perspective wasn't super difficult, but what it did is it created a homogeneous infrastructure between all of the different providers that they were working with, both on-prem with VMware, AWS, and GCP. And so with that allows operations. I'd mentioned previously that operations, when you're doing multiple different clouds, can be a nightmare if you don't have some level of common between all of them. So this gives us that ability. So here's the kind of the final deck. I kind of grayed out the AWS one because it's less important now. But yeah, we actually run this cluster over a couple different zones, which is nice. So we do have some high availability built into the clustering of the application, or I'm sorry, of the Slurm cluster. And along with it, we have a lot of attached storage that ends up working with that. All the different systems run over a VPN back into the general networks so that you have accessibility to the data back in HQ. So ongoing challenges, we kind of alluded to the fact that Slurm itself as a product doesn't have dynamic clustering, or it does not have dynamic scale. You can't just throw a new machine into the cluster and have it auto-recognize. Google did do a product, like I said, that does kind of help with that, but it's not public yet. Or the press release is, but the code isn't. So another challenge is, identity management is another one too that we are still, making sure we try to stay on top of. Identity management, like IAM in general. So what boxes have access to what data, what researchers have access to what. Right now we have a very, very generic policy that is maybe a little too permissive. But it's a challenge because you have to match that up with AWS and also what you're doing with your on-prem. So, all right. So at the very end, so what did we do by going through all of this? One, we took the existing solution that Michael and his team put together. I would say we strengthened it in certain ways. We brought in a lot of Dev9's best practices on how we put together infrastructure as code, how we run it. And so we kind of strengthened that. So we did help out the AWS and also the on-premise version of the cluster. But by virtue, we also added the capabilities for Google. We were able to now provide a 50-50 split for Google and AWS traffic for cloud, which now means that they can scale even larger. The amount of data, as you saw, like 1.2 petabytes of data, that's a lot of data. So having that, they now have the capacity or the capability of growing that even larger as they need and matching the same amount of compute that they need or the demand they have. They don't have a lot of resource contention now. So. All right, so in the future, we are looking at adding in the capabilities of using Genomics API along with any of the other machine learning. The hosted TensorFlow, right now a lot of the researchers are using TensorFlow, but it's the self-managed, and it's non-GPU based, obviously no TPUs. So it's still very early days for that, but it's a lot of the data they're doing doesn't necessarily require, but it's something where they want to start being able to use it. So we're expanding the solution to be able to add those types of capabilities to it. Also, right now, all the data, as we mentioned, is on-premise, but also all the compute is generally in the US. Fred Hutch has multiple centers around the world, and so being able to actually use this same solution, because we've now created this infrastructure as code, we can now create that same infrastructure in multiple different regions around the world and still have the same infrastructure for them. And then the last thing is, it's a hope, but we'd like to actually be able to add in some preemptive machines as well to this to kind of help lower the cost. And a lot of that's going to come with the synchronization and the automation that we're doing for identifying when you want to build new cluster or add more to a cluster and redeploy it. So we're working on some of those pieces, but that will be kind of a fun next step for us.